Welcome to Frequency Matters, the RF and Microwave Update series. This is a special episode. I'm Pat Hindle. I'm here with my co-host Eric Heim. Special guest, Sean Darcy, Senior Director of Aerospace and Defense at Infineon Technologies. Welcome, Sean.
Hey, thank you guys. Appreciate it.
It's great to work with you again. We've done a lot of stuff like the BNS podcast together. So happy to have you on the show. And I know you've been doing a lot of work in the aerospace and defense markets, especially the satellite market. So can you tell us what trends you're seeing in the satellite market and how power products are factoring into that?
Oh, sure. And thank you again for having me, guys. So I think the first thing I'd like to talk about is the change we're seeing from the traditional rad-hard space. Big satellites, primarily government-funded satellites, where the focus is on creating a very high-value asset that may take 3, 5, 7 years between the time you start cutting metal to the time you launch it. And now we're starting to see a transition from that to these high-density constellations. If you think about this, was started by SpaceX. They made the first big change in the industry. But now that's starting to be adopted by people like the U.S. government, for example, Space Development Agency, where you have Tranche 1, 2, 3, 4, where you're going to be launching hundreds, if not thousands, of satellites to support military and government, type of missions. I think something else that is just recent, we've seen things like, NVIDIA is starting to try to fly some of their products. And this is a part of a trend we're seeing towards trying to do a lot more edge computing on orbit. For most of the time that we've had satellites and satellite missions, what we've done is the satellite, of course, goes around the Earth, collects the information, the data it wants, and then when it comes over the United States, you actually transmit the data down. Nowadays, some modern technologies, both imaging and even things you do in RF and microwave, you can't either keep all that data, store all that data, or even process that data, let alone transmit it. So we're seeing a huge move towards how much of that processing can be done on orbit. That's a huge change. It's a significant increase of power, a significant increase in the thermal constraints you're going to have and the thermal challenges. I think those are two of the biggest trends. The other big trend, of course, we all see, and is one of my favorite, you guys ever seen me before, I talk a lot about this, is how people are starting to adopt phased array. Phased array for a long time was very difficult on orbit because of power budget, also because of radiation susceptibility of the components they had, and everything else went in that signal chain. Now you saw, again, people like SpaceX, some of the other communication companies started to be able to deploy these phased arrays. A lot of challenges with the phased array in orbit, right? For a long time, people went with just anywhere from 1 to 3 just mechanically steered dishes or mechanically steered arrays. But the problem is you cannot provide the connectivity to the ground that's required for some of the new missions people are trying to do. A good example is when people are trying to do handset direct to satellite. A lot of us been in the RF world, not the power world, but in the RF world, that's a huge gain problem. Yeah. You got a 3-watt transmitter trying to get up 1,200 nautical miles. The only answer to that is phased array. So I think that's the other big thing. We're still in the infancy of that. Some people have tried it. It's been a very difficult thing on orbit, but I think in the next 5 years, that'll be the dominant way we're actually communicating.
So you mentioned rad-hard a moment ago, and what does the radiation environment look like to a satellite, and how do those conditions influence that decision for radiation hardened versus radiation tolerant?
Oh, good question. So let me break it down into maybe, there are multiple orbits. Let's look at basically 4 different orbits. Most people are familiar with a LEO, low Earth orbit, equatorial type of orbit. The inclination is small, so it may go around the Earth maybe 30 degrees. But primarily, that's a lot of satellites. That gives really good coverage across the equator. They're easy to launch. One of the big challenges when you go away from an equatorial LEO orbit is the fact that now you have to spend a lot of fuel to put it into a different orbit. If you launch, for example, from the equator, it's very easy. You're already going 26,000 miles an hour just by going straight up. So let's look at that. That's LEO, low Earth orbit. Another one that a lot of people are confused about is polar orbit. That is an orbit that actually goes around the poles. It has a very different radiation profile. The third one I would say is MEO, which is mid-Earth orbit. That's where most of the GNSS or GPS, Galileo type satellites are, about 11,000 miles up. And then the ones that are probably unique from those three are those in GEO, which is geostationary. So those are satellites, for example, that are launched that sit over the same place on Earth all the time, but they're not protected by this wonderful thing called the Van Allen belts. The Van Allen belts are part of the magnetosphere that goes around the Earth and provides a lot of protection from subatomic particles. But to my point about polar orbits, the reason the aurora borealis is up north like that is because that is where it collapses and readmits some of the energy. So when you look at a LEO satellite, you might be able to get away with very, very low environmental screening. If you look at a rad-tolerant part, which is what a lot of these are aimed towards, you may only need 30 K-rad TID, which is total ionizing dose. Might not be a problem. Your Cepheid or your MEV, you might be down 26, 27. And also you may have a design that's very redundant, so I can reset that satellite very frequently. So that's a very different environment. When you start going into a polar orbit, which actually comes in and out of the Van Allen belts, now you have to actually start asking a difficult question, which is how much rad tolerant can you do? And now what might have to be rad hard? One thing I'll talk about maybe a little bit later is this hybrid between rad tolerant and rad hard. MEO is one of the most challenging. These are because of where they are in orbit and the function they do, you're looking at something that now you're up back in the rad hard, the 100 K rad, very high TID. You have to be very careful of Cepheid. The other thing is you think about it, guys, most of the things again in MEO are things like GPS satellites. These are very, very expensive assets. And as you guys know, it is very difficult to go up and fix something. The number of satellites that I think have ever been fixed is about 7 or 8. And usually that was when we had the space shuttle. We don't have that anymore. So the reliability on something like that is paramount. You only have 24 to probably 30 of those satellites in existence. Finally, geostationary, really do not quite have the exact same radiation effects profile as like a deep space probe, but they get very close. So now you're in the full rad hard profile. Almost all the parts have to be rad hard. But I'll tell you something interesting is people have actually tried to fly automotive plastic in that orbit. Going to have to see how that works. There are other things you can do to protect those electronics. You can put them in a vault, you can shield them, etc. So hope that helps.
Absolutely.
Good answer. Yeah. So in your experience, what are the key challenges to integrating radiation tolerant parts on the power side into that satellites, and how do you kind of address those challenges?
So great question, and really plays off what we were just talking about. One of the challenges in rad tolerant is you have really a slightly less reliability. You're probably not going to put rad tolerant in a very high value asset. So a lot of people look at the radiation requirement by orbit. I encourage people not to do that. Look at the radiation requirement by the value of the asset and the value of the mission. If I only need something that's going to fly for a couple months, I really don't care. If I need something that's going to be a very high value asset, it's got to detect a very key event, and I need an orbit for 10 years in LEO, I'm going to need radiation hardened. So back to your question though, so part of the rad tolerant is it's a very complex thing about a system. When we actually have to build satellites on the building side of it, it is a set of calculations of probability of failure of hundreds of components. Rad tolerant, you're going to do a trade space, maybe not against cost, but how fast you can get the technology. It takes a bit of time to qualify a new technology as rad hard, much less to rad tolerant. So it's not always a cost play. But the other thing is what in that system can be rad tolerant and what has to be rad hard. So for years, people have done things that are called like a guard card. So a guard card is something that is very, very rad hard, sits in your space VPX chassis, very reliable. You can count on that thing probably the last 15, 20 years without fault. But what it allows you to do is put much lesser environmental cards in the chassis, and then the guard can actually reset them if they latch up or if they have an issue. It's a good example where the challenge is. Right now, I think people are still trying to figure out how far does that pendulum swing into rad tolerant before you at least have to have something rad hard. So your main power bus, do you really want that rad tolerant? Right, something that's a stepping down the voltage, your DC to DC converter, in something that's going to a very key payload. Do you want a transient effect? Can you risk that? Now you still may be rad hard. So it's still a trade space. I think it's evolving.
So what about thermal management? What strategies would you suggest if someone wants to use silicon or GaN power components in a satellite power system?
Oh, good question. I will say that I appreciate that question, because one of the things I find is interesting is people new to space focus on radiation. Always focus on radiation. For you guys who are new to the industry, probably a bigger challenge in radiation is thermal. There is no convection in space. It's conduction, and then you have to radiate your heat overboard as infrared. So thermal becomes a huge, huge challenge, probably more so than any other challenge in space. I think the good thing about what you want to look at with things like, especially new technologies like GaN technology, you have much higher efficiencies, you're radiating less heat. Something that goes back to we make the choices is silicon carbide, which we make, still does very, very well. So the big thing about the thermal challenge is how do you actually do the thermal budget across the entire satellite? I always like to say that I think a lot of, I spent most of my career actually on the customer side, not on the semiconductor side. I think most people will agree, it was on the customer side. We don't care if it's made of silicon carbide, bubblegum, or GaN. We care about the efficiency and how well it works. Those of us in semiconductors care about that, but really does the customer really care about that? He wants something very efficient. I think something else that we get very good in the space industry is derating things. And we derate parts so that we drive them at very low temperatures. We also do that for radiation effects, but we also do that to manage thermal. Finally, the other thing, regardless of the technology, is how you do your duty cycle. People can figure out very quickly as the satellite goes around the Earth, and when it's in eclipse, it's not generating electricity, it's running off batteries. The other thing is how do you actually manage your thermal in the exact same cycle? When you're on sun side, you're absorbing a lot of energy, a lot of heat. When you're on eclipse side, it's a little bit different. So, but it's a very difficult challenge. It's probably, like I said, it's more difficult than actually the radiation.
So what are the implications of radiation on the performance and reliability of power products when you integrate them in satellite systems? And, how do you overcome that?
So radiation effects, manifest themselves in various ways. Probably the most well-known is total ionizing dose. That comes in LDR, low dose rate, HDR, high dose rate, mid dose rate. They have a lot of doses that they do this. And they try to map that to the orbit or the radiation exposure that system's going to see. But it doesn't always map one-to-one. So how things fail on ionizing dose, kind of your question on technologies, GaN fails a little bit different than silicon, than silicon carbide, than SiGe by CMOS. I mean, when you start going through the technologies, now you actually do have different failure modes and susceptibility to ionizing radiation. You have to be aware of that. And so the other thing is, kind of like you're talking about challenges, is you have to be careful not to design a system where the weakest link is something that you have wonderful parts around it. You really get up to maybe 500K rad, and you have one part that's going to go to 50K rad.
Yeah, doesn't do any good. It won't work.
Now, when you do risk calculation, that's your weakest link. So that's one thing you have to consider when you design. The other thing we always look at is SEFI effects, or single event effects. These are sometimes single event bursts. The part actually fails 100%. A lot of times it's things where they flip a bit, or it's a single event latch. Something latches up. Could cause a transient, cause spike, cause you could lose memory. Those are interesting in the fact that as long as it's not permanently damaging the part, you can mitigate for that. Part of the design is actually you can either do where you're doing redundant, no common failure mode, or you can do things where you're actually polling. A lot of the older digital systems, when I was young, we designed them, we actually were polling against memory. We were looking against registers and CPUs. We may have 4 things interrogating each other. As we're getting better parts, you look at, people like BAU, the RAD 750 type, just wonderful, really super reliable type computer board. You don't have to do that kind of design anymore. They've taken care of that for you. The other challenge, is occasionally you do get secondary particle effects, secondary particle interactions. Geosatellites can have some pretty strange things. Mass corona ejections, things like that can impact those satellites. It's kind of rare. And you do try to protect your critical avionics, again, within a vault, if you have to. The other thing, of course, within radiation is the slow degradation. Parts that just are impacted by radiation over a period of years, and then you have a slow, hopefully graceful degradation. If you can map again amplifiers, the dBMs bleed off, and it's predictable, I can use that part to build a satellite. If it's not predictable in the way it degrades, that's really bad. So you can design for that. And like you said, like thermal, things like that. Yeah. The other big challenge for the components in space is you're in a vacuum. None of us design our parts. All of us have been on the bench. I don't think any of us ever worked in a vacuum. I don't think we'd survive in a vacuum. So that's also a really different thing that actually does degrade electronics over time. So,
So in your experience, how do the challenges of cost and device integration influence the final system design, that final satellite power system, and maybe specifically from a mission objective standpoint and a budget constraint standpoint?
I wish there was an easy answer to that, right? There is a huge trade space in the system engineering world between cost and mission duration. And there's no easy way to get around that. Like I was talking about before, you do these huge risk calculations and you do your PDR, your primary, and you go to CDR, which is your critical design review. A lot of time is spent trying to figure that out. I mentioned something about guard cards. These are, I think you are going to see these hybrid designs where I've got a rad hard set of electronics that control very critical functions. And you can spend money there because these are going to be probably 5 to 10 times what the rad tolerant part is. Then on the other hand, you can actually have your rad tolerant. If you think about basically putting things in an LRU card slot, you have the main controller is going to be rad hard. But now you have these rad tolerants that you can actually just control. If there's a risk, it can mitigate it. Or you think about it, if there's a big enough cost delta, I can put 3 or 4 cards in there. And when one fails, I can use another. Yeah. That's something new in the satellite world, but it's actually doable. The other thing I think you're going to see is these hybrid card designs, where you're rad hard, you're rad tolerant. And as much as people find it surprising, people are starting to look at things like automotive parts. And again, it goes back to this thing that so many people focus on cost and don't realize that one of the big drivers is I need to get the technology in orbit right away. A good example is if I'm going to put a satellite in orbit to listen to somebody, and all of a sudden they get really good and they're 94 to 96 gigahertz, and that's where they're transmitting on, I need to get something on orbit pretty quick that listens there. I can't wait for somebody to go, a super het design sitting on orbit is going to weigh a ton and kill me. Yeah. But, how do I actually go and get a set of high-speed converters, digitizers, transceivers? Can I really wait 5 years for them to do the metal spins and the changes make them rad hard? Or can I put a rad tolerant asset up there and just use the rad hard stuff to protect it? So,
well, Sean, thank you for this. This has been a great amount of really interesting information.
Thank you.
And to our viewers, please check out more videos on videos.microwavejournal.com. And please subscribe and like us. And thanks for watching.